Welcome back, deep divers. Today, we're diving headfirst into a mystery that even Einstein couldn't quite wrap his head around.
It's a real brain twister, that's for sure.
It's the quantum world, and specifically, something Einstein called spooky action at a distance.
Ah, yes, spooky action. The heart of the quantum debate, really.
And we've got three incredible papers to help us navigate these murky waters.
We've got some heavy hitters in the quantum world joining us for this dive.
First, we'll tackle Einstein, Podolsky, and Rosen's 1935 paper, where they basically said, hold on, is quantum mechanics really all there is?
They weren't convinced, not one bit.
Then we'll hear from Niels Bohr with his rebuttal, where he drops this mind-bending concept called complementarity.
Complementary, think of it like, well, imagine trying to clap with one hand. You kind of need both, right?
I like that analogy.
Mm-hmm.
And finally, we'll fast forward to 1982 and dig into the experiment by Aspect, Delabard, and Roger, which basically put all this theory to the test.
They put it all on the line to see who was right, Einstein or Bohr. A real showdown.
All right, so before we get too far, let's make sure everyone's on the same page. What exactly is this spooky action that had Einstein so spooked?
Well, it all boils down to this idea of entanglement. Imagine two particles linked in such a way that they share the same fate no matter how far apart they are.
So it's like they're connected by some invisible string. You tug on one and the other one twitches.
Exactly.
Mm.
And here's the kicker. This connection, this entanglement, it's instantaneous. You measure one particle here and boom, you instantly know something about the other particle, even if it's light years away.
Okay, I can see why Einstein called it spooky. It does seem to defy some pretty basic notions about cause and effect, right?
Right, and that's what had Einstein and his buddies scratching their heads. They said, look, if you can instantly know something about one particle by measuring the other, even across vast distances, then something's fishy.
So they basically said, this can't be how reality works.
Exactly. They argued that there must be something deeper going on, something we're missing.
Okay, so let's dig into their paper. Where did they even begin to unpack such a mind-boggling concept?
Well, they started by laying down the law, so to speak. They said, for any theory to truly describe reality, it has to be complete. And by complete, they meant that for every element of physical reality, there should be a corresponding element in the theory.
So like a one-to-one map. If something is real, it should be represented in the theory, right?
Exactly. But then they added a crucial twist. They said, okay, but what qualifies as an element of physical reality? And they came up with this rule. If you can predict the value of something with absolute certainty without disturbing the system in any way, then that thing must be a real element of reality.
Okay, let me see if I've got this straight. They're saying, if I can figure something out about a system, like, say, the momentum of a particle, without actually messing with it, then that momentum is a real part of the system, not just some theoretical construct.
Exactly. It has to be a real, tangible property of that particle.
Okay, that seems reasonable enough. But I'm guessing this is where things start to get a bit tricky, right?
You bet. Let's go back to our entangled particles. Say, we measure the momentum of one of these entangled particles. Because they're linked, we immediately know the momentum of the other particle, even if it's miles away. No problem.
Yeah, that's the spooky action we were talking about.
Right. But now, according to their own rule, since we can predict the momentum of the second particle without actually touching it, disturbing it, that momentum must be a real element of reality, a real property that the particle possesses. But, and here's the catch, quantum mechanics, specifically Heisenberg's uncertainty principle, says you can't know both the position and momentum of a particle with perfect accuracy at the same time. So if we've just nailed down the momentum of our second particle, its position becomes inherently uncertain. We can't know both at the same time.
Hold on a second. So they're saying because we know the momentum, we can't know the position. Isn't that just a limit of our ability to measure things? Kind of like trying to weigh a feather on a bathroom scale? It's not that the feather doesn't have a weight. It's just that our tool isn't precise enough.
Right. That's what you might think. And that's what a lot of physicists thought at the time. But EPR, they argued it was something much deeper, a fundamental limitation baked into the fabric of reality. This uncertainty wasn't about our tools, it was about the inherent fuzziness of the quantum world itself.
Okay, so if I'm following their logic, they're saying that because we can predict the momentum without actually disturbing the particle, its momentum is a real thing, a real property of the system. But the uncertainty principle says we can't know both momentum and position perfectly. So are they saying that the position of the particle isn't real?
That's the crux of their argument. They're essentially saying that if quantum mechanics was the be-all and end-all of describing reality, then the position of that second particle shouldn't be considered real because we can't know it for sure. But their own definition of elements of reality suggests the position must be real since we know the momentum. It's a catch-22.
So it sounds like they've painted themselves into a corner. They've got this paradox where their own definition of reality clashes with what quantum mechanics tells us.
Exactly. And they concluded that this paradox, this contradiction, was a big red flag. It meant that something was missing. Quantum mechanics, as it stood, must be incomplete. There had to be some hidden variables, some deeper level of reality we weren't seeing, that could account for both the position and momentum, even if we couldn't access both simultaneously.
Okay, so they're saying there's more to the story than quantum mechanics lets on. It's like we're looking at a blurry photo, and they're saying there must be a sharper image hiding beneath the blur.
That's a great analogy, and that was the essence of their argument. They weren't necessarily saying quantum mechanics was flat out wrong, but rather that it was an incomplete picture of reality.
Okay, so Einstein and his crew threw down a pretty serious gauntlet, suggesting that the quantum world is even weirder than we thought.
It was a challenge to the entire physics community, really.
But didn't Bohr have something to say about all this?
Oh, he did. And that's where things get even more interesting. But before we jump into Bohr's response, I think it's worth pausing for a moment to appreciate what EPR achieved with their paper. They didn't just poke holes in quantum mechanics, they offered a whole new way of thinking about reality, one that would shape the debate for decades to come.
It was a real game changer. They forced everyone to really confront the meaning of reality, what it means to observe and measure, and whether our everyday intuitions about the world even apply at the quantum level.
Right. They took us from the lab to the realm of philosophy, forcing us to ask some pretty deep questions.
All right, so we've got this paradox, this mystery laid out by EPR, and now Bohr is about to step into the ring with his own interpretation. This is getting good.
So EPR laid down the challenge, questioning the very foundations of quantum mechanics.
They really shook things up.
And now it was Niels Bohr's turn to step up to the plate and defend quantum mechanics.
I can imagine Bohr pacing back and forth, muttering to himself, "Oh, Einstein, you think you've got me cornered."
And his response, oh, it was brilliant. Bohr didn't back down, not one bit. He met EPR's arguments head on, but instead of searching for these elusive hidden variables, he offered a completely different perspective.
So what was Bohr's secret weapon? How did he plan to counter EPR's challenge?
He introduced this revolutionary concept called complementarity.
Complementarity. It sounds a bit, well, intimidating. Can you break it down for me? What exactly did Bohr mean by that?
Sure, think of it like this. Imagine you're looking at a coin, a simple everyday coin.
All right, got my coin. What now?
You can focus on its head side, or you can flip it over and examine its tail side, but you can't see both sides at the same time, right?
Right, makes sense. You can only see one side at a time.
Exactly. They're like two sides of the same coin, complementary aspects of a single object.
Okay, so how does this coin analogy apply to the quantum world? What are the heads and tails in this scenario?
Well, Bohr argued that in the quantum world, certain properties of a system are like the two sides of our coin. They can't be known simultaneously with perfect accuracy. It's like the universe is playing a game of hide and seek.
Interesting. So which properties are we talking about here?
Think back to the EPR paradox. They were hung up on position and momentum. You know, where a particle is and how fast it's moving.
Right, right. The whole knowing one means you can't know the other conundrum.
Precisely. And Bohr said this wasn't just a limitation of our instruments or a reflection of our ignorance. It was a fundamental truth about reality.
So it's not that the information is hidden, it's that the universe itself won't let us see both sides of the coin at the same time.
You got it. And that's complementarity in a nutshell. It's like the universe is saying, hey, you can pick which aspect of reality you want to focus on, but you can't have both at once.
It's like trying to focus on two things at once. You end up blurring both of them.
Yeah. Or imagine squeezing a balloon. If you press on one side, the other side bulges out.
Okay, I think I'm starting to wrap my head around this complementarity thing. But how did Bohr use this to address the EPR paradox?
Well, Bohr didn't just answer their question, he reframed the entire debate. He shifted the focus from whether a property-like position was real or not to what it even meant to talk about a particle's position in an entangled system.
So he was basically saying, hold on, let's take a step back and reconsider what we even mean by these concepts.
Exactly. You see, EPR, they assumed that a particle had a definite position. even if we couldn't measure it precisely. Kind of like that coin. Even if you're only looking at heads, you assume tails is still there on the other side.
Right. It's a pre-existing property, independent of whether we observe it or not.
But Bohr, he challenged this assumption. He said, no, no, no. In the quantum world, the position of a particle doesn't really exist in a definite way until it's measured. It's not that the particle is hiding its position. It's that the position isn't really defined until we interact with the system and force it to choose a value.
Whoa, so he's saying the act of measurement is what brings the property into existence.
It's one way to think about it. It's like the particle exists in this fuzzy, indeterminate state, a superposition of possibilities, and only when we measure it do we force it to collapse into a definite state.
Mind blown. So in essence, he's saying EPR's whole argument is based on a faulty premise, that these properties exist independent of our measurement.
That's the heart of it. They assumed we could know the momentum without disturbing the system, but Bohr said, no, 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 the very act of measuring is a disturbance, it's an interaction. And that interaction, that measurement, forces the system to choose a specific momentum. And in doing so, we make the position uncertain.
Okay, so it's not about missing information. It's about a fundamental shift in how we understand reality. We can't just assume our classical intuitions apply in the quantum world.
Exactly. And that's the genius of Bohr's response. He didn't try to squeeze quantum mechanics into a classical box. He embraced the strangeness and offered a completely new framework for thinking about reality at the quantum level.
He didn't just win the argument, he changed the rules of the game. So is that it? Did Bohr's response settle the debate?
Well, not quite. You see, while Bohr's arguments were compelling, they were still, well, theoretical. The debate raged on, and physicists on both sides were eager for a more definitive answer.
Enter the aspect experiment, right? That's where things get real. But before we dive into that, I think we need to take a quick break. Let our listeners digest all this mind-bending quantum mechanics. All right, so we've got Einstein and his crew throwing down this challenge, suggesting quantum mechanics is hiding something.
They really pushed the boundaries of our understanding.
And then Bohr comes along with this idea of complementarity, completely changing the game.
He turned the whole debate on its head, didn't he?
But it sounds like the aspect experiment was the final showdown.
The ultimate test to see whose vision of reality would reign supreme.
Okay, so how did they actually put these ideas to the test? It's not like they could ask an electron to pick a side, right?
Well, not exactly. The aspect experiment focused on a specific prediction of quantum mechanics called Bell's inequalities.
Bell's inequalities. Sounds a bit like a mathematical tongue twister.
They might sound complicated, but they're essentially a way to differentiate between what standard quantum mechanics predicts and what theories with hidden variables, like the ones EPR favored, would predict.
So it's a way to say, if the universe follows quantum mechanics, we should see these results. But if hidden variables are pulling the strings, we'll see something else.
Exactly. And the aspect experiment was a brilliant way to test which set of rules the universe was actually playing by. They used entangled photons, those tiny particles of light, and measured their polarizations. You can think of polarization as the direction the light wave is wiggling.
So they're measuring these wiggling light particles that are somehow connected, even if they're far apart. It sounds pretty high-tech.
It was cutting-edge stuff for the time, and to make sure they were really testing quantum mechanics and not some other sneaky effect, they had to be incredibly clever.
What do you mean?
Well, for instance, they had to rule out the possibility that the two entangled particles were somehow secretly communicating with each other, which would explain the spooky action.
Ah, so Einstein thought there might be some hidden communication going on faster than light, like some kind of cosmic Morse code between the particles.
Exactly. So Aspect and his team rapidly switched the measurement settings while the photons were in flight, ensuring there was no time for any sort of signal to travel between them.
That's amazing. So they're essentially outsmarting the universe, closing all the loopholes to make sure the results were truly a reflection of quantum mechanics in action.
Precisely. And that's why the Aspect experiment is such a landmark. They went to extraordinary lengths to make sure their experiment was a fair test, a true reflection of reality.
All right, enough with the suspense. What were the results? Was it Einstein or Bohr who emerged victorious?
Well, drum roll, please.
Yeah.
The results showed a clear violation of Bell's inequalities.
So they were siding with quantum mechanics.
Exactly. It was a major blow to the idea of local hidden variables and a stunning confirmation of the strangeness of the quantum world.
Wow, so they actually proved that spooky action at a distance is real. Measuring one particle can instantly affect another, even if they're light years apart.
That's the inescapable conclusion. The aspect experiment and many subsequent experiments have provided overwhelming evidence that the universe, at its most fundamental level, doesn't always play by the rules of classical physics.
So where does that leave us? Does this mean Einstein was wrong?
It's not so much that Einstein was wrong, it's more like his intuition, which had been shaped by decades of working with classical physics, just couldn't fully grasp the depths of the quantum realm.
The universe, it turns out, is even weirder and more wonderful than he imagined. So after this incredible journey, from Einstein's doubts to Bohr's radical ideas and the mind-blowing aspect experiment, where do we go from here? What are we supposed to do with this knowledge that the universe is fundamentally stranger than we thought?
Well, I think the biggest takeaway is that we shouldn't be afraid to question our assumptions. We should embrace the mystery, the strangeness, and let it guide us to new discoveries.
So this isn't just about some abstract debate in physics. It's about expanding our understanding of the universe and our place within it.
Absolutely. And who knows what other mind-boggling secrets the quantum world still holds. The journey of exploration is far from over.
That's the beauty of science, isn't it? There's always another layer to uncover, another question to ask.
Exactly. And the more we learn, the more we realize how much we still don't know. But that's what makes it so exciting. There's always something new to discover.
Well, I think we've given our listeners plenty to ponder today. We've covered a lot of ground, from the foundations of quantum mechanics to the philosophical implications of entanglement and the groundbreaking aspect experiment.
It's been quite a journey. We've challenged our intuitions, explored the boundaries of reality, and hopefully sparked a sense of wonder about the universe and the mysteries it holds.
So to our listeners out there, keep questioning, keep exploring, and never stop diving deep. Who knows what incredible discoveries await us in the quantum realm?
Until next time, keep those minds curious and stay tuned for another deep dive.
See you all on the next dive.